All right, in this video, we're going to finish up BC Homework 9.3. So we're going to look at some and kind of quickly decide if they're going to converge or diverge based on the antiderivative. So integral from 0 to 1 of 1 over the square root of x dx, that's x to the negative half. Okay, well, I know if I take the antiderivative, that'll be 2 times x to the half as x runs from 0 to 1. And 0, with 0, the issue is division by 0, and I'm not going to see any division by 0 when I take the limit as the lower bound approaches 0. So I'm going to say this one converges. Right, and let's kind of keep moving. To b is going to be the integral from 1 to infinity of 1 over the square root of x dx. Okay, so I rewrite as power 1 to infinity x to the negative half. When I anti-differentiate, I get x to the positive half divided by a half. As x runs from 1 to infinity, infinity is the thing that I'm going to have to take the limit of. Well, I'm going to be taking the square root of infinity, and that's going to also go to infinity. And so I'm going to say this one diverges. The next one, I'm going to rewrite this as another power x to the negative 5 over 4. If I anti-differentiate that, I'm going to add 1 to the power. So add 4 fourths is still negative 1 fourth, and let it run from 0 to 1. Well, if I've got a negative power of 0, that's division by 0. So I know that that's not going to work, and I know this one's going to diverge. So let's see, it diverges. D, I'm going to say, okay, 1 to infinity of 1 over x to the 5 fourths. That's where I can rewrite. Anti-differentiate. I definitely did not divide by the new power on that old one, but it still didn't change whether or not it was going to converge or diverge, right? So I'm going to add 1 to the power and divide by the new power. So I have an actual antiderivative. And then when I'm going to plug in, when I let the upper bound run towards infinity in the denominator, that's okay. That goes to 0. You're dividing by a huge number that leaves you with a really small number. So this one's going to converge, because this is also, I could, instead of writing it as negative 4x to the negative 1 fourth, I could write it as negative 4 over the fourth root of x. And then as x runs towards infinity, I'm going to be getting closer to dividing by huge numbers, closer to 0. Okay. And so I'll say this one converges. Room here. Okay, 2e is going to be the integral from 4 to 6 of x minus 5 to the negative 3/7 power. Okay. The issue is the 5, which is in the interior of the interval. So I'm just going to have to think about, okay, I'm going to have to split this up into the integral from 4 to 5 plus the integral from 5 to 6. Okay. So I'm just going to work on one of these integrals to figure out whether or not this integral converges or diverges. Then we'll work on the one on the left. I'm going to anti-differentiate by adding 1 to the power. That's not 3. That's x minus 5. Add 7/7 to the power, so I get 4 over 7. Okay. And I'm going to divide by the new power. I forget this time. And I'm going to let x run from 4 up to 5. Okay. Since the power became positive when I anti-differentiated, when I plug in, as x approaches 5, well, I'm just going to get closer and closer to taking 0 to the 4/7 power, which is going to be 0. So this one's going to converge. What would happen is, okay, I would take this one all the way down if I needed the value. I would take this one all the rest of the way. I would take this one the same distance, and then I would add them together. But since I know that one of them converges, I know that both of them are, their sum is going to converge. So I will say that this one converges. the integral from 6 to infinity of the same thing. That one's going to diverge because when I anti-differentiate, well, I guess I can go over here and anti-differentiate x minus 5 to the 4/7 divided by 4/7. Okay, as I let x run towards infinity, since when I anti-differentiated, the power became positive, a positive power of infinity, it's like infinity in the numerator. It's going to go to infinity. And so I'm going to say that this diverges. Right. Too far there. And 2g is going to be the integral from 2 to 4 of 1 over x squared minus 6x plus 9. I can factor that. That's x minus 3 squared. So again, I'm going to have to split this up into two separate integrals because the vertical asymptote is happening in the interior of my integral. So x minus 3 to the negative 2 plus the integral from 3 to 4 of also x minus 3 to the negative 2. Okay. This one, I'm going to anti-differentiate, add 1 to the power, divide by the new power, let x run from 2 to 3. But as x gets closer and closer to 3, I'm getting closer and closer to dividing by 0. And so I know that this one's going to diverge. When I take that limit and I try to actually plug stuff in, I'm going to say it diverges. All right, the next one is going to be 2h, saying, okay, integral from 4 to infinity of the same thing, 1 over x minus 3 squared. And so, well, I took a break after that last one, so I kind of forgot how this went. Okay, yeah, I'm going to anti-differentiate, add 1 to the power, divide by the new power. Okay, this is really, instead of the negative 1 power, I could say this is negative 1 over x minus 3. As x goes from 4 to something really large, I'm going to take the limit. And we know that as x gets really large, negative 1 over x minus 3 goes towards 0. And I'm going to say that this one converges. All right, and then one more, 2i, the integral from 1 to 2 of x plus 3's square root. This isn't even an improper integral. This is a trick question. This one's going to converge because there's no division by 0. Wait, I guess it's negative half. But still, I would need to be taking x equals negative 3 or going out to infinity for this to be an improper integral. So I'm just going to say it converges. All right, the next one is saying, let R be the region between the graph of f equals e to the negative 2x and the x-axis for x greater than or equal to 3. Find the area of R. So I'm going to integrate from 3 to infinity. Okay, so I'm going to take an antiderivative.
I am not that excited. Well, I kind of am, but shut up.
And I'm going to let x run from 3 towards infinity. And that will be the limit as the upper bound goes towards infinity of negative 1/2 of 1 over e to the 2b minus negative half of 1 over e to the 6. And then I know this one's going to be, that's going to go to 0, that fraction I've highlighted. That's going to go to 0. And so I'll be left with positive half of 1 over e to the 6. So this amount of area is equal to 1 over 2e to the 6. This next one is related to a multiple choice question that I'm familiar with. And it's giving you basically integrate from 1 up to x, here's what you're going to get in terms of x. Like they already did the anti-differentiation step for you. They plugged in top and bottom and subtracted, and that's what you're going to get. So what you need to remember is, okay, if you're integrating from 1 to infinity, that's the limit as the upper bound goes to infinity of the integral from 1 to b. And this is, well, that's just going to be the limit as b goes to infinity of 3b over square root of 16b squared plus 1 minus 1. We know how to compute that limit. Okay, these are essentially the same on top and bottom because square root of 16b squared, that's basically 4 times the square root, I mean, not square root, 4 times the absolute value of x. So this is going to have a ratio of 3/4 as b approaches positive infinity. So it would be 3/4 minus 1. And it's going to be negative 1/4. Here's another one that I'm familiar with that's related to a multiple choice question. And this is like best case scenario for us. We hope that if we're tested on improper integration, this is what it looks like. Because what we know is that this is going to be, okay, you find an antiderivative. That's easy enough. Let it run from 1 to infinity. This is where we transform to a limit. The limit as x approaches infinity of h of x, they told us is 6. So this is equal to 6 minus negative 2 is 8. And we can definitely do that one. Okay. Now we're interested in what values of p, what kind of exponents are going to make this integral converge. So what we're going to do, we're just going to kind of treat it like we did before. Turn it to a negative power. And I'm realizing it might be a good idea if I distributed that negative 1 power. Or negative 1 to the 3p plus 1. So it'd be negative 3p minus 1. Okay. And so if I wanted to take an antiderivative, I would add 1 to the power. Okay, negative 3p minus 1 plus 1 is just going to be negative 3p. And I'm going to divide by the new power. And we're interested in x running from 1 to infinity. And then at this point, we transform to a limit. Obviously, p had better not be 0, okay? Because if it was 0, I'd be divided by 0 at this point, and that would not be good. If p was equal to 0, taking x to the negative first power, and, well, we already know that one diverges because we showed it in class, and we've probably run into that example more than once, that the integral from 1 to infinity of 1 over x dx, that's infinite. So, let's say b goes to infinity, 3p, I'll factor that out, times 1 over b to the 3p, and actually, you know what? I'm going to call this b to the negative 3p. And minus 1 to the negative 3p. No, it's just going to be any power of 1 is 1. Okay. Now for this to converge, when I let b go to infinity, I need this to be a negative exponent, right? I need really b to be in the denominator as it's going to infinity in order for it to converge. So I'm going to take this and I say, I need negative 3p to be less than 0. I need to have that negative exponent. And so that would be when p is greater than 0, right? If I divide both sides by negative 3, it's going to reverse the direction of the inequality. Okay, so it's p needs to be greater than 0 in order for that original integral to converge. Okay. This one is an integral up against a vertical asymptote that I need to figure out, what powers are going to make this converge. If you already know the rule, like about which powers make integrals converge against vertical or horizontal asymptotes, you can just feel free to use that rule. I'm not including that in my class this year. I'm just going to kind of work them all as they come, and then we'll talk about that when we go and study infinite series later on in the course. But for me, I know I need to rewrite this just like the other one. Okay. I'm going to anti-differentiate. Add 1 to the power, divide by the new power. Okay. And then so that's going to equal limit as the lower bound approaches 0 from the positive side of over negative 2p plus 4. I'm going to factor that out, just make it a little easier. 1 to the negative 2p plus 4 minus a to the negative 2p plus 4. Okay. The problem here comes when that power is negative, right? So I take 0 to a negative power, I'm dividing by 0, and that's not good. That's going to cause the integral to diverge. So what I need is for this negative 2p plus 4, I need this to be a positive power. So I'm just taking 0 to a positive power, which is just going to be 0, and it'll cause my integral to converge. So I need this to be positive. Okay, if it was equal to 0, then we would have a problem right there. And back to that other one, we know that the integral from 0 to 1 of 1 over x, that doesn't exist either. So it's going to need to be strictly greater than 0. We start solving, p is less than 2. And those will be the values of p that make the integral converge. This next one is a multiple choice question I found in an AP classroom. I found it a little interesting. Okay. And so I think I want to just look at this and I'd say, like, why is this an improper integral, right? We can have division by 0 when x is equal to 0. Okay. So here, when x equals 0, causes division by 0. And that's going to make it an improper integral, but as we know, that does not mean that the integral automatically diverges. So I'm saying that C is kind of got to be out, right? And, well, I guarantee you A is out as well, because that's just way too good to be true. Right? And so we're kind of down to B and D. It's like, does this integral exist, or does it not? And we know how to deal with this. So the first step, find an antiderivative. X runs from, wait a second, because it's in the interior of my interval, I need to be, bless you, need to be splitting this up into 2 separate integrals. Pardon me. Negative 2 to 0 of this plus the integral from 0 to 2 of this. But if you've done enough of these, you know that you can work one of them to see if it converges, and whatever happens with the one will happen with the other. So, all right, I'm going to move this back up. So this is antiderivative, top and bottom. Okay, when I go to plug in 0, that was the troublesome spot. So I need to take the limit as the upper bound approaches 0 from the negative side, in this case, of minus the log of the absolute value of e to the negative 2 minus 1. Okay. This limit right here does not exist, because the closer that b gets to 0, the closer I get to taking the log of 0. Log of 0, that doesn't exist. Okay. And so that limit fails to exist, so the integral diverges, and so that would be answer choice D. Because the limit of the antiderivative doesn't exist, that's why the integral diverges. All right, number 9 and 10, these are just, reviewing some rules that you just need to know. Okay, this last one right down there, the derivative of log with base 2 and argument x, that you probably don't need to know, but the other 4 you do need to know for AP Calculus. And so you're thinking, the things you just need to know. I'm not going to go in and show you why these are true today. If you want to know why, you can come ask me, or you can kind of search my YouTube channel. I've got explanations for all these things. But I'm just going to kind of throw in the derivatives here, and there you have it. Okay. So these are ones that we need to know, especially the arc-trig derivatives for the next lesson. So that's why I put those on this homework. Just kind of refresh your memory about those and remind you that these are things we are expected to know. Okay, the last one is just some antiderivatives that we need to be able to do. Okay, the sine of 2x, I need to be able to know an antiderivative for sine of a thing and know what to do with that 2. Okay, with secant squared and cosecant squared, these are trig antiderivatives that we just got to recognize. Oh, secant squared x, that's the derivative of tangent of x. And cosecant squared x, that's not exactly the derivative of cotangent, but it's close enough that I can figure it out. Here we know that the derivative of cotangent is negative cosecant squared, so I just need to figure out how to deal with that negative. And the antiderivative of 2 to the t with respect to t, we just need to kind of think backwards to the chain rule, or just remember that that's going to require us to divide by the natural log of 2. So here you go. Here are those antiderivatives, and I've for this video. Thanks for watching.